This video will be about catalysts and how they can increase the rate of reaction. Okay, so we should know from previous experience that catalysts increase the rate of reaction and that they're not consumed in a reaction. Instead, they are regenerated unchanged to be used again and again. Okay, but the question now and what this is going to focus on is how do they do this? How do they actually affect an increase in rate of reaction on a reaction? So what they do is they reduce the activation energy, or what we sometimes refer to it as the MKE, the minimum kinetic energy required in a collision for it to be successful. They reduce that bar for a reaction by adding steps to something we call a reaction mechanism. And we're going to focus on reaction mechanisms in a subsequent video, but this one will focus on catalysts exclusively. Okay, so again, examining the function of a catalyst through the lens of a potential energy diagram, and oops, I need to make sure I label that correctly, a potential energy diagram, EP. What we can show here is that we should be familiar by now with the idea that the activation energy of the forward reaction is going to be the height from there to there. So this would be the activation energy for the regular, let's say, uncatalyzed reaction. So we're going to say the green line is for the uncatalyzed regular reaction happening. And then we can add another line to this to show what would happen if we added a catalyst. So if we added a catalyst, what would happen is we would see two smaller humps. We turn that one hump camel into a two hump camel. And in doing that, we would actually make the new activation energy for the reaction the height of the highest of those two smaller humps there. Okay, so this would be for the catalyzed reaction. So as mentioned in the previous slide there, we can see that what a catalyst actually does is it turns a one-step process into a two-step process, and it lowers the activation energy for the reaction. Now, also notable here is that notice that the position of the initial reactants here and the final products here did not change in any way as a result of using the catalyst. In other words, we might say that like the delta H for this reaction is the same no matter what. Okay, so delta H is unchanged when you use a catalyst. The actual beginning and final potential energy positions of the reactants and products have not changed in any way, so there's no change in the actual delta H or the heat or enthalpy for the reaction. But what we see is that let's call it the EA cat, the activation energy in a catalyzed reaction is always less than the activation energy in the uncatalyzed reaction. So the catalyzed reaction proceeds faster. Catalyzed reaction proceeds faster. Greater proportion of the molecules would have enough kinetic energy upon collision to overcome that lowered activation energy barrier. One extracted question you might have about what was shown on that previous potential energy diagram is how does it actually make it faster when it turns that one hump into two humps? How does that work, and what does that mean? Well, basically what it's suggesting is that instead of happening in one big step where we have a large activation energy to overcome, it happens in two smaller steps, and each of those respective steps has a lower activation energy than the original uncatalyzed one. So even though it's adding extra collisions to the process, like now instead of having just one collision here, we need to have two collisions down here, each of those respective collisions has an activation energy that's lower than the original, so this would happen faster. So it really doesn't matter how many steps are in the mechanism, as we're going to see. What matters is the height of the highest mountain that has to be climbed in the mechanism. That's what controls the rate of the reaction. So this is how a catalyst works.